Hey there, friend. If you're here to unwind and drift into sleep, you've found the right place. Dim your screen, lower the volume, breathe slowly, and welcome, especially if you're new here. Let's begin. Chapter 6: The Personal Implications, Infinite Versions of You. The most personally profound implication of many worlds' interpretation is what it means for you, your identity, your choices, and your future. Right now, as you process these words, countless quantum events are occurring in your brain and body. Neurons are firing or not firing based partly on quantum processes. Chemical reactions in your cells depend on quantum tunneling probabilities. Every one of these quantum events creates branching. There are versions of you in different branches experiencing slightly different thoughts, making slightly different decisions, living slightly different lives. The you that you experience, the singular perspective you identify as yourself, is just one branch among countless others containing other versions who are equally convinced they're the real you. This raises immediate questions about personal identity. What makes you you? Is it your memories, your personality, your physical body, your continuity of consciousness? In a branching universe, all these criteria become ambiguous. There are branches where you have slightly different memories, because quantum events affected which neurons encoded which experiences. There are branches where your personality developed differently, because quantum randomness influenced critical moments in your neural development. There are branches where your body is slightly different because quantum events during cell division created different mutations. And yet all these versions arguably have equal claim to being you. Philosophers have long debated personal identity through thought experiments. If you were gradually replaced neuron by neuron with artificial components, would you still be you? If your brain were copied atom for atom, which copy would be you? Many worlds transforms these thought experiments into physical reality. You are being copied constantly through branching, and all the copies are equally real. They diverge over time as different quantum events accumulate, but they share your history up to the branching point. Are they different people, or are they all versions of a single person distributed across branches? The standard answer from many worlds advocates is that personal identity should be understood through branching structure rather than unique individuals. Before a branching event, there's one person. After branching, there are multiple people who share the same past. Each one will subjectively feel like they're the continuation of the pre-branch person, and they're all correct. Personal identity is a relation of continuity through branching rather than a property of isolated individuals. You're not a single entity persisting through time. You're a branching structure, a tree of related experiences and perspectives connected through quantum causation. This view has radical implications for how we think about our lives. Your past is relatively unified, a single trunk with relatively few major branches. But your future is vastly diverse, containing countless branches where different versions of you experience different outcomes. When you make a decision, you're not choosing between futures. You're determining the relative weights of different future branches, making some more likely or higher amplitude than others. But all the branches that are quantum mechanically possible actually occur. Consider what this means for a simple choice. You're deciding whether to turn left or right at an intersection. Classically, you make one choice and follow one path into the future. In many worlds, quantum events in your brain probably influence this decision, perhaps through thermal fluctuations that affect neural firing or quantum processes that affect neurotransmitter release. If the decision involves any quantum randomness, reality branches. In some branches, you turn left. In others, you turn right. Both versions of you experience making a free choice, and both are equally real continuations of the you that existed before the choice point. Most of the time, these branches remain very similar. Whether you turned left or right at one intersection usually doesn't matter much in the long run. The branches reconverge toward similar futures. You end up in roughly the same place, doing roughly the same things, regardless of minor decision variations. This is why the world seems classical and predictable, despite underlying quantum branching. Most quantum events don't have macroscopic consequences. They create vast families of nearly identical branches that appear to follow deterministic laws, but occasionally quantum events have enormous consequences through chaotic amplification. A cosmic ray strikes a particular DNA base at just the right moment during cell division and causes a mutation that leads to cancer, or doesn't strike and you remain healthy. A neuron fires during a critical moment of decision-making and you accept the job offer, or doesn't fire and you decline. These rare but important quantum events create branches where your life trajectory diverges significantly. In some branches you stay healthy, marry your partner, have children, and live to old age. In other branches, you get sick, relationships fail, different opportunities arise, and your life follows completely different paths. The butterfly effect magnifies small quantum differences into large classical differences. The flap of a butterfly's wings in Brazil might not literally cause a tornado in Texas, but it's true that tiny changes in initial conditions can produce vastly different outcomes in chaotic systems. Weather is chaotic. Neural dynamics are chaotic. Economic and social systems are chaotic. This means quantum events, which create tiny initial differences between branches, can lead to dramatically different macroscopic outcomes as the chaos amplifies small variations. Your brain is particularly susceptible to this amplification because it's a complex, dynamical system operating near critical points. Neurons are poised on the edge of firing or not firing. Small fluctuations can tip them one way or the other. These individual neuron firings affect which thoughts occur to you, which associations form, which decisions feel right. The accumulation of countless quantum events in neural processes creates substantial variation across branches in your thought patterns and choices, even though the underlying quantum effects are tiny. Think about an important decision you made in the past. Maybe you chose which college to attend, which job to accept, whether to move to a new city, whether to start or end a relationship. These decisions involved conscious deliberation, but they also involved subconscious processes affected by your brain's quantum substrate. If quantum events influenced the decision, there are branches where you made different choices. Those branches contain versions of you living the lives you didn't live, experiencing the futures you didn't experience, becoming the people you didn't become. This isn't just speculation about what might have been. In many worlds, those alternate versions of you actually exist. They're as real as you are, living in branches as real as yours, equally convinced they made the right choice or regret they made the wrong one. The person you might have been isn't a counterfactual possibility. It's an actual person in another branch of reality. Your current identity is just one outcome in a vast probability distribution of possible yous that all exist simultaneously across the branching structure. Some versions of you made better choices than you did. There are branches where you were braver, where you took the risk that led to success, where you said yes to the opportunity that changed everything. In those branches, you might be more successful, happier, more fulfilled than the version of you reading these words. But there are also branches where you made worse choices, versions where you took risks that backfired, where you trusted the wrong people, where things that could go wrong did go wrong. In those branches, you might be struggling more, suffering more, wishing you had made different decisions. The question of how you should feel about these alternate versions is philosophically complex. Should you care about them? Are they you in any meaningful sense? Or are they different people who happen to share your past? If you could somehow know what's happening in other branches, would you feel pride in the successful versions or shame about the failed ones? Would you feel relief that only one version is you, or regret that you can't experience the better lives some versions are living? Many world's advocates suggest we should feel a kind of distributed existence across branches. Your identity isn't localized to a single branch, but spread across all branches containing your continuations. The successful versions are you succeeding. The suffering versions are you suffering. You exist in all these states simultaneously from a perspective outside any individual branch. Only from within a particular branch does it seem like you're a single person with a unique history and future. This creates an interesting relationship with regret and satisfaction. You might regret a decision you made, wishing you had chosen differently. But in many worlds, you did choose differently in other branches. There are versions of you who made the choice you wish you'd made. Does this provide comfort? It might reduce the sting of regret to know that at least some versions of you got the better outcome. Or it might increase the pain to know that you personally aren't in those branches, that you specifically made the worst choice, even though other versions of you made better ones. The concept of quantum immortality emerges disturbingly from many worlds' logic. Imagine you're in a life-threatening situation where survival depends on quantum randomness. Perhaps you're diagnosed with cancer, and quantum events will determine whether treatment succeeds. In some branches, the quantum events favor treatment success, and you survive. In other branches, they don't, and you die. From an external perspective, both outcomes occur with probabilities determined by the quantum amplitudes. But from your subjective first-person perspective, you can only experience the branches where you survived. This leads to the unsettling conclusion that you might subjectively experience surviving arbitrarily unlikely events. No matter how many potentially lethal quantum events you face, there are always some branches, however unlikely, where you happen to survive them all. You can only experience branches where you remain alive to have experiences. This seems to suggest that, from your subjective viewpoint, you're functionally immortal. You'll always find yourself in whatever branch you survived into, no matter how improbable. Most physicists think quantum immortality is either wrong or meaningless. The branches where you survive unlikely events have extremely low amplitude, so they're less real or less significant in some sense. Moreover, mortality usually doesn't depend primarily on quantum randomness. Classical causes dominate most deaths. A car accident at high speed isn't a quantum event. Aging is driven by thermodynamic processes, not quantum branching. While quantum events might occasionally make the difference between life and death, they're not the primary determinant of survival for most people in most situations. But quantum immortality does highlight how many worlds changes the meaning of survival and death. When you die in some branches but survive in others, what happens to your consciousness? The consciousness in dying branches ends. The consciousness in surviving branches continues. From the inside, each branch's perspective persists or terminates. There's no single answer to whether you survive because you're not a single entity, but a branching structure, some of whose branches end while others continue. This raises profound questions about what death means in a branching universe. When someone you love dies, they die in your branch. But there are other branches where they survived, where quantum events played out differently, where they continue living. Does this provide consolation? The person you specifically knew and loved in your branch is gone. The versions in other branches had different experiences after the divergence point, became slightly different people, lived different continuations of their life. They're simultaneously the same person, sharing the history you remember, and different people, having experienced a different present and future. Some people find many worlds comforting regarding death. You don't completely cease to exist. Branches of you continue, and in some high-amplitude branches, you might live much longer than in others. Your consciousness persists in those branches even after it ends in this one. But this comfort is limited, because the you in this branch, with these specific experiences and relationships, will still end. The continuation is in branches you can never access, lived by versions you can never meet, experiencing futures you'll never know. The question of how quantum branching relates to free will has generated extensive philosophical debate. In many worlds, the universe is deterministic at the level of the universal wave function. Given the quantum state at one time, the Schrödinger equation predicts it at all future times with certainty. There's no randomness in how the universal wave function evolves. This seems to eliminate free will if free will requires indeterministic universes where multiple futures are genuinely possible. But many worlds advocates argue this conclusion is too quick. While the universal wave function evolves deterministically, individual observers within branches experience what feels like free choice. You deliberate, weigh options, make decisions. The fact that all outcomes occur doesn't negate the reality of your decision-making process. You're not choosing between futures in the sense of making some possible and others impossible. You're determining which branches you'll inhabit, which versions of yourself will experience which outcomes. This is compatible with free will if free will is understood compatibilistically, as the ability to act according to your desires and reasoning without external compulsion. When you make a choice, you're doing what you want based on your values and beliefs. The fact that other versions of you make different choices in other branches doesn't undermine the authenticity of your choice in your branch. Each version freely chooses according to their state of mind at the decision point, and all the choices are real. The many worlds picture might even enhance free will in a certain sense. In a single universe deterministic framework, there's one future that will happen regardless of what you think or do. Your choices are links in a causal chain that produces an inevitable outcome. In many worlds, all possible outcomes actually occur. Your choices don't determine a single future, but do determine the distribution of futures across branches. The consequences of your decisions are real across the full branching structure, not just in one predetermined timeline. The relationship between choice and quantum branching becomes more subtle when you consider that most choices probably involve quantum randomness only minimally. when you decide to have coffee rather than tea. This decision involves neural processes that have some quantum component, but it's primarily driven by classical factors like your preferences, habits, and current physiological state. The quantum contribution might be small. If so, there are branches where you chose differently, but they're low amplitude, less significant in the overall branching structure. This suggests a spectrum of choice types. Some decisions are heavily determined by classical factors with minimal quantum contribution. The branching around these choices is narrow, with most high-amplitude branches making the same choice. Other decisions are more balanced, where quantum events in your brain play a larger role in tipping you one way or the other. These create broader branching with substantial amplitude across different choice outcomes. The subjective experience of difficult decisions, where you genuinely could go either way, might reflect genuine quantum ambiguity in your neural state. Your life trajectory can be visualized as a path through the branching tree of reality. You started from a relatively unified trunk, your conception and early development. As you grew, quantum events in your body and brain created increasing branching. But most branches remained close together, experiencing similar childhoods with minor variations. At key decision points, especially ones involving genuine uncertainty or quantum randomness, the branching spread wider. You chose a college or career, moved to a new place, started or ended relationships. Each major choice point corresponds to wider branching, where your life paths diverged more dramatically. Looking forward from your current moment, your future is a vast tree of possibilities. Some branches lead to long, healthy lives with success and fulfillment. Others lead to tragedy, illness, early death. Most fall somewhere in between, living ordinary lives with ordinary joys and struggles. All these branches exist with probabilities determined by quantum amplitudes. You can't control which specific branch you'll experience, because you'll experience all of them, each version of you convinced they're experiencing the one true outcome. What you can control is how you act in this branch, which affects the probabilities and shapes the branching structure. If you make healthy choices, exercise regularly, avoid unnecessary risks, you increase the amplitude of branches where you thrive, and decrease the amplitude of branches where you suffer consequences of poor decisions. The outcomes still branch across all possibilities, but your choices shift the weight toward better branches. In this sense, your choices matter exactly as much as they seem to. They don't determine a single future, but they do shape the distribution of futures you'll experience across branches. This leads to practical wisdom about living in a branching universe. You should make choices as if this branch is the only one that matters, because from your perspective within the branch, it is. The fact that other branches exist doesn't reduce the importance of living well in this one. You can't access those other branches, can't experience their outcomes, can't help the versions of you in different branches. Your responsibility is to this branch, this version of yourself, this continuation of the consciousness that's reading these words right now. At the same time, many worlds provides perspective on success and failure. If you fail at something in this branch, there are branches where you succeeded. This doesn't excuse failure or eliminate responsibility, but it contextualizes your individual outcome within a larger structure, where all possibilities actualize. You're not uniquely cursed if things go badly, nor uniquely blessed if things go well. You're simply experiencing one realization from a probability distribution that includes both good and bad outcomes. The implications extend to how we think about personal narratives and life stories. We naturally think of our lives as single, coherent stories with beginnings, middles, and endings. We construct identities around our unique experiences and choices. But in many worlds, your life isn't a single story, but an anthology of stories, all branching from the same origin, each taking different paths through possibility space. The you that you experience is one story in this anthology, but it's not privileged or more real than the others. It's simply the one you happen to be experiencing from inside. This might seem to diminish the significance of your individual life. If there are countless versions of you, what makes this particular version special? But many worlds advocates suggest the opposite conclusion. Every branch is special precisely because all branches are real. Your experiences, your choices, your life matters not, despite the existence of other branches, but alongside them. The full reality of who you are includes all the branches, the totality of possibility that the quantum mechanics says must exist. You're not diminished by having other versions. You're enriched by being part of a vast branching structure, exploring every path your life could take. Chapter 7. Cosmic and Existential Implications. The scope of quantum branching extends far beyond individual human lives to encompass the entire history of the cosmos. Every quantum event that has ever occurred, from the Big Bang to this present moment, created branching. The universe you inhabit is one branch in an incomprehensibly vast structure that includes all possible histories consistent with quantum mechanics. To understand the full implications of many worlds, we need to zoom out from personal experience to cosmic scales and consider what branching means for the origin, evolution, and ultimate fate of reality itself. The Big Bang, the moment when our observable universe began its expansion from an extremely hot, dense state 13.8 billion years ago, wasn't a single event, but a quantum event. The early universe existed in a quantum state with all possible configurations in superposition. As this initial quantum state evolved according to the laws of physics, it branched continuously. Every quantum fluctuation in the primordial plasma, every particle interaction in the dense early cosmos, every decay of unstable particles created branching. The universe split into countless versions, differing in the precise details of how matter and energy were distributed in those first moments. Most of these branches remained very similar because quantum fluctuations in the early universe were tiny compared to the average density. The cosmic microwave background radiation we observe today shows these fluctuations as temperature variations of about 1 part in 100,000. These tiny differences in the primordial density field grew through gravitational amplification into the galaxies and large-scale structures we see today. But, in different branches, the quantum fluctuations were slightly different. Some branches have galaxy clusters in slightly different locations. Some have individual galaxies that formed earlier or later than in our branch. Some have galaxies that never formed at all in certain regions. The quantum uncertainty in the early universe means there's no single definite history of cosmic evolution. There are countless branches where the quantum fluctuations played out differently, leading to different arrangements of matter throughout space. In some branches, the Milky Way galaxy formed slightly differently, with more or fewer stars, with our solar system in a different location or not existing at all. In some branches, conditions on Earth were slightly different, affecting whether life emerged and how it evolved. Every cosmic history that's consistent with the laws of physics and the initial quantum state actually occurred in some branch. This creates a natural explanation for the fine-tuning problem that has puzzled cosmologists and philosophers. The fundamental constants of nature, values like the strength of gravity, the mass of the electron, the cosmological constant, appear to be precisely calibrated to allow complex structures and life to exist. If these constants were even slightly different, stars wouldn't form, or chemistry wouldn't work, or the universe would expand too quickly for galaxies to coalesce. The probability of randomly getting constants that allow life seems astronomically small, leading some to invoke design or the anthropic principle to explain our existence. Many worlds provides a different perspective. If the constants themselves are determined by quantum processes in the early universe, then they branch across different values. There would be branches with every possible combination of fundamental constants that quantum mechanics allows. Most of these branches are sterile, with constants that don't permit interesting structure. But some branches have constants in the narrow range that allows stars, planets, chemistry, and life. We necessarily find ourselves in one of those life-permitting branches, because observers can only exist in branches where conditions allow observers to evolve. This is a form of anthropic reasoning, but it's anthropic reasoning grounded in the physics of quantum branching rather than in mysterious selection principles. We observe fine-tuned constants, not because the universe was designed for us or because we're specially lucky, but because there are many branches with many different constants, and we can only observe from within branches compatible with our existence. The vast majority of reality might be lifeless, with constants that don't permit complexity, but pockets of observer-compatible branches exist within the overall branching structure. The connection to eternal inflation theory deepens these implications. Inflation was a period of exponential expansion in the very early universe, lasting perhaps 10 to the minus 32 seconds, during which the universe grew by a factor of at least 10 to the 26. This rapid expansion explains why the observable universe is so uniform and flat. But inflation driven by quantum fields has a remarkable property. In some regions, the inflation field decays and inflation ends, creating a bubble of normal expanding space-time like our observable universe. In other regions, inflation continues, and these regions themselves spawn more bubbles. This process of eternal inflation means new bubble universes are constantly forming, each potentially with different physical properties. Combined with many worlds' quantum branching, this creates a truly staggering multiverse. First, there's quantum branching within our bubble, creating countless branches differing in the outcomes of quantum events. Second, there are other bubbles created by inflation, potentially with different vacuum states and different effective physical laws. Third, within each bubble, there's further quantum branching. The total structure includes every possible bubble universe and every possible quantum branch within each bubble. Max Tegmark has classified this as a Level 2 multiverse from eternal inflation and a Level 3 multiverse from quantum branching, both existing simultaneously. His Level 1 multiverse consists of distant regions beyond our cosmic horizon, where different random events occurred, which is less radical because it only requires the universe to be larger than we can observe. But levels 2 and 3 together create genuine diversity in physical laws and quantum histories, producing a reality far vaster and more varied than our observable universe. The measure problem becomes especially acute in this context. With infinitely many branches and potentially infinitely many bubble universes, how do we calculate probabilities? If every possible outcome occurs infinitely many times across the full structure, what does it mean to say one outcome is more probable than another? Cosmologists working on this problem propose various solutions involving how to weight different regions of the multiverse. But the question remains philosophically challenging and mathematically subtle. The arrow of time, the fact that time flows from past to future rather than being symmetric, might be explained by the branching structure. We remember the past, but not the future, because the past is relatively unified, a single trunk of shared history that all branches emerged from. The future is diversified across countless branches, each containing different outcomes. Your current state contains information about past events through causal traces and memories, but it doesn't contain information about future events because those events haven't been determined yet, in the sense that they split across multiple branches. Thermodynamically, entropy increases from past to future, and this increase defines time's direction. The second law of thermodynamics, which says entropy tends to increase, might be related to branching structure. As the universe evolves and branches, the quantum state becomes more complex, with more components representing different macroscopic configurations. This increase in branching complexity could be connected to the increase in thermodynamic entropy, both reflecting how initial simple states evolve into complex, diverse states over time. The ultimate fate of the universe takes on new meaning in many worlds. In standard cosmology, we can calculate the universe's future based on its current state and the laws of physics. With the observed positive cosmological constant, the universe will continue expanding forever, with galaxies moving away from each other, stars eventually exhausting their fuel, matter decaying on extremely long timescales, and the cosmos approaching a cold, dark state of maximum entropy called heat death. This fate seems depressing, but it's based on following a single timeline forward. In many worlds, there isn't a single future, but a branching structure of possible futures. Most branches probably do lead to something like heat death, because the second law of thermodynamics applies to almost all branches. But there might be extremely low-amplitude branches, where quantum fluctuations conspire to decrease entropy locally, creating temporary pockets of order in an otherwise decaying cosmos. These branches would be staggeringly unlikely, but if the branching structure is sufficiently rich, they exist somewhere in the full quantum state of the universe. Some physicists speculate about branches where intelligent civilizations learn to manipulate the fabric of space-time itself, potentially escaping heat death by creating new regions of space-time or accessing other bubble universes. This is wildly speculative, but many worlds at least allows for the logical possibility. In a sufficiently vast branching structure containing all quantum possibilities, even outcomes with infinitesimal probability amplitude appear in some branches. Whether these branches are significant, given their tiny amplitude, is another question. The cosmological constant problem, the mystery of why the vacuum energy density is so much smaller than quantum field theory predicts, might be addressed through many worlds combined with inflation. If different bubble universes have different vacuum energies, and we necessarily observe from a bubble compatible with our existence, the small observed value might be anthropically selected. Most bubbles with large vacuum energies either collapse immediately or expand too rapidly for structure to form. Only bubbles with small vacuum energies like ours permit the long, slow evolution needed for galaxies and life. But this explanation is controversial because it seems to give up on deriving the cosmological constant from fundamental principles. Instead of calculating why it has its observed value, we're saying it could have many values across different bubbles, and we observe a life-compatible value because we can't exist in bubbles with incompatible values. Some physicists find this satisfying as an explanation. Others see it as a retreat from physics' traditional goal of deriving all observable parameters from deeper principles. The quantum mechanics of the entire universe raises fascinating questions that many worlds handles naturally. In Copenhagen interpretation, an external observer is needed to collapse the wave function. But the universe as a whole has no external observer. What collapses the universal wave function? Copenhagen has no good answer. Some variants suggest consciousness plays a special role, but this seems to require conscious observers existing outside the universe, which is metaphysically bizarre. Many worlds avoids this problem because the universal wave function never collapses. It evolves according to the Wheeler-DeWitt equation, a version of the Schrödinger equation for the entire universe. This equation describes how the quantum state of all matter, energy, and space-time geometry evolves. Solutions to this equation represent different possible cosmic histories, all existing as components of the universal wave function. Observers within the universe experience particular branches, but the total quantum state includes all branches without any collapse occurring. The wave function of the universe is an extremely abstract object. It's not a wave in ordinary three-dimensional space, but a wave in configuration space, an infinite-dimensional space representing all possible arrangements of all the matter and energy in the cosmos. Each point in this configuration space represents one complete specification of where every particle is and what every field is doing throughout all space. The universal wave function assigns amplitudes to different regions of this configuration space, determining which cosmic configurations are more or less likely. This abstract mathematical object somehow contains all of physical reality, every galaxy, every planet, every living being, every thought you've ever had exists as part of the structure of this wave function. When we say reality branches, we mean the wave function has components corresponding to different macroscopic situations, and decoherence prevents these components from interfering. The branches aren't separate universes in different locations. They're different components of a single mathematical object that describes all existence. The holographic principle, derived from black hole physics and string theory, suggests that all the information in a region of space can be encoded on its boundary. The three-dimensional interior of a region is fully described by two-dimensional information on its surface. This bizarre result might indicate that three-dimensional space itself is emergent, somehow derived from more fundamental two-dimensional quantum information. Combined with many worlds, this suggests reality might be even stranger than we've imagined, with both spatial dimensions and branching structure emerging from deeper informational or computational substrate. Some physicists working on quantum gravity propose that space-time itself is woven from quantum entanglement. The geometry of space, the distances between points, the curvature that we experience as gravity all emerge from patterns of quantum entanglement between fundamental degrees of freedom. If this is correct, then the branching structure of Many worlds isn't just branching in time across different histories. It's also branching in the structure of space itself, with different branches having slightly different space-time geometries, emerging from different entanglement patterns. The relationship between quantum mechanics and general relativity remains one of physics' deepest puzzles. General relativity describes gravity as curved space-time, treating space and time as a smooth, classical continuum. Quantum mechanics describes everything in terms of discrete quantum states and probabilistic evolution. These frameworks are mathematically incompatible in extreme situations like black hole interiors or the Big Bang singularity. A complete theory of quantum gravity would unite them into a single, coherent description. Many worlds might be important for quantum gravity because it provides a fully quantum mechanical description of reality without requiring classical concepts, like wave function collapse. If space-time itself is quantized and subject to quantum superposition, the many worlds framework might naturally accommodate space-time branching into different geometric configurations. Different branches could have different space-time geometries, with observers in each branch experiencing one particular geometric structure as their reality. Black holes present special interpretational challenges. When matter falls into a black hole, what happens to its quantum information? Hawking's calculation suggests black holes evaporate through quantum radiation, but this radiation appears thermal, containing no information about what fell in. This contradicts quantum mechanics' principle that information is never destroyed. In many worlds, the information isn't destroyed but distributed across branches in complex ways we don't yet understand. The branching structure might preserve information even when it appears classically to be lost. The question of whether our universe is typical or atypical within the many-world structure has generated extensive discussion. If we could sample randomly from all branches, weighted by their amplitudes, would we expect to find ourselves in a branch like ours? This relates to anthropic reasoning and to probability in many worlds. We should expect to observe what typical observers in typical branches observe. If our observations are highly atypical, this might indicate a problem with the theory or our understanding of probability in branching universes. Some physicists have proposed that we can make predictions using typicality. For example, we might predict how long our civilization will survive by estimating where we fall in the distribution of all civilizations across all branches. If most civilizations survive for certain durations, we should expect to be in a civilization with typical duration. But these arguments are controversial because it's unclear how to count branches or weight them appropriately. Different weighting schemes give different predictions about what's typical. The cosmic microwave background radiation provides a window into the early universe and potentially into branching structure. The tiny temperature fluctuations we observe in the CMB were created by quantum fluctuations during inflation. These fluctuations are the branching points where different cosmic histories diverged. By studying the statistical properties of CMB fluctuations, we're learning about the quantum state of the early universe and the branching structure that emerged from it. Some researchers have looked for anomalies in the CMB that might indicate interactions between branches. If branches could influence each other under special circumstances, we might detect signatures in cosmological observations. The so-called cold spot in the CMB, a region colder than expected, was briefly hypothesized to be evidence of another universe colliding with ours. Most cosmologists think it's just a statistical fluctuation, but it illustrates how observational cosmology might potentially test multiverse ideas. The scale of cosmic branching is difficult to comprehend. Every quantum event in every atom, in every star, in every galaxy creates branching. The universe contains about 10 to the 80 atoms in the observable region. Each atom undergoes countless quantum interactions every second. Even conservative estimates suggest the branching rate is enormous, with the number of branches growing faster than any conceivable exponential function. After nearly 14 billion years of cosmic evolution, the branching structure has become vast beyond any human ability to visualize or quantify. Yet all these branches are described by a single wave function, a single mathematical object evolving according to a single equation. The unity underlying diversity is remarkable. The universal wave function contains every possible cosmic history, every possible arrangement of matter and energy, every possible outcome of every quantum event that ever occurred. This single object, existing in abstract mathematical space, somehow is the totality of physical reality, containing galaxies and stars and planets and life and consciousness and everything we experience, or could experience. The many worlds interpretation thus transforms cosmology from the study of a single universe's history into the study of a branching structure containing all possible universes consistent with the laws of physics and the initial quantum state. Our observable universe is one branch among countless others, distinguished not by being special or unique, but simply by being the branch we happen to inhabit. The cosmic story isn't a single narrative, but an anthology of all possible narratives, each playing out in different branches of the universal wave function. This perspective addresses fundamental questions about existence in unexpected ways. Why is there something rather than nothing? Perhaps because the mathematics of quantum mechanics requires a non-trivial wave function, and that wave function contains all possible somethings through its branching structure. Why do we observe these particular laws of physics? Perhaps because we're in one of the branches compatible with observers, among many branches with different laws. Why does the universe seem fine-tuned for complexity and life? Perhaps because fine-tuning isn't universal but branch-specific, with most branches being lifeless, but some branches having conditions that permit observers to ask these questions. Chapter 8. Consciousness, Free Will, and the Observer. The relationship between consciousness and quantum branching raises questions that probe the deepest mysteries of existence itself. What happens to your consciousness when reality splits? Do you somehow divide into multiple consciousnesses experiencing different branches? Or does consciousness follow one branch while copies exist in others? Can you feel the split occurring? Why does your subjective experience seem singular and continuous when the many worlds interpretation says you're constantly branching into multiple versions? These questions touch on the hard problem of consciousness, the puzzle of why subjective experience exists at all and how it relates to physical processes. When a quantum measurement occurs that causes branching, both the measured system and the observer become entangled and enter superposition. Before the measurement, you're in a definite state, about to observe a quantum system in superposition. After the measurement, the combined system of you plus the quantum system is in superposition. There's a component of the wave function where you observed spin up, and another component where you observed spin down. Each component contains a complete version of you, with a complete set of experiences and memories, differing only in what measurement result they observed. From an external perspective, if such a perspective were possible, both versions of you exist simultaneously as different components of the universal wave function. But from your internal subjective perspective, you only experience one branch. You see one measurement result, not a superposition of results. Your consciousness feels singular, localized to one branch, unaware of the other branches containing other versions of you having other experiences. This asymmetry between external description and internal experience is at the heart of the consciousness problem in many worlds. Why don't you experience superposition? If your brain state enters superposition after a measurement, with one component having seen spin up and another having seen spin down, why don't you simultaneously experience both outcomes? The answer involves decoherence and the structure of consciousness itself. Decoherence causes the different components of your brain state to become entangled with the environment in incompatible ways. The version of you that saw spin up is entangled with environmental states corresponding to that observation. The version that saw spin down is entangled with different environmental states. These two components can no longer interfere quantum mechanically. This environmental entanglement effectively isolates the branches from each other. Your consciousness in each branch is embedded in that branch's environment and cannot access information from other branches. The version of you in the spin-up branch has neural states, bodily states, and environmental interactions all consistent with having observed spin-up. The version in the spin-down branch has states consistent with having observed spin-down. Each version has a complete and coherent experience of having made one definite observation, even though the universal wave function contains both versions simultaneously. The unity of consciousness, the feeling that you're a single unified subject of experience rather than multiple disconnected experiences, persists within each branch. Because decoherence happens so quickly for neural states, your brain is a warm, wet, electrochemically active system, constantly interacting with its environment. Any quantum superposition of significantly different brain states decoheres in less than a femtosecond. This means you never experience being in superposition, because the decoherence timescale is vastly faster than the timescale of conscious experience. By the time any conscious processing occurs, decoherence has already separated the branches. But this raises a subtle question about the relationship between physical branching and subjective experience. Physical branching occurs when decoherence happens, which is continuously throughout your body and brain, as quantum systems interact with environments. Yet you experience a continuous stream of consciousness, not a discrete series of branching points. How does continuous physical branching produce continuous subjective experience? The answer might be that consciousness is associated with patterns of information processing in the brain that persist across branching. Each version of you in each branch experiences consciousness because each branch contains a brain performing the information processing that underlies conscious experience. The hard problem of consciousness asks why physical processes produce subjective experience at all. Why is there something it's like to be you, to see colors, to feel pain, to think thoughts? Physical theories describe matter and energy, forces and fields, but nothing in these descriptions obviously requires the existence of subjective experience. Many worlds doesn't solve this hard problem, but it does provide a framework for thinking about how consciousness relates to physical reality. If consciousness arises from information processing in brains, and brains are quantum systems that branch along with the rest of reality, then consciousness must branch too. Each branch contains a consciousness, experiencing one possible outcome of the information processing. The mystery isn't why consciousness branches. It's why consciousness exists at all in any branch. That's the hard problem, and it's equally mysterious in all interpretations of quantum mechanics. Many Worlds simply says that whatever produces consciousness in one branch produces it in all branches where the necessary physical structures and processes exist. Some theories propose that consciousness plays a special role in quantum mechanics, causing wave function collapse or selecting which branch becomes real. The most famous advocate of consciousness causes collapse was Eugene Wigner, who suggested that consciousness is qualitatively different from other physical systems and follows different rules. In his view, measurement by a conscious observer causes genuine collapse, while measurement by unconscious apparatus merely creates entanglement. This preserves a special status for consciousness, but creates enormous conceptual problems. At what point does a system become conscious enough to cause collapse? Do animals cause collapse? What about insects or bacteria? Many Worlds avoids these problems by denying that consciousness has any special role. Consciousness doesn't cause branching, or prevent it, or select which branch continues. Consciousness is simply one type of physical process that occurs within branches. When branching happens, consciousness branches along with everything else. There's no privileged status for conscious observation versus any other type of physical interaction. A measuring device causes branching through decoherence, whether or not anyone consciously observes the device's reading. The branching occurs when the device becomes entangled with its environment, not when someone looks at the device. This democratic treatment of consciousness as just another physical process appeals to physicalists who think consciousness must ultimately be explained in terms of brain activity and information processing. But it leaves the hard problem untouched. We still don't know why certain types of information processing produce subjective experience. We can describe the neural correlates of consciousness, the brain states associated with different conscious experiences, but we can't explain why these neural states feel like something from the inside. The Penrose-Hameroff theory of quantum consciousness proposes that quantum coherence in brain microtubules, structural proteins inside neurons, plays an essential role in consciousness. They suggest that consciousness involves quantum computation occurring in microtubules, and that objective collapse of these quantum states through gravitational effects produces moments of conscious awareness. This theory is highly controversial. Most neuroscientists think the brain is too warm and noisy for significant quantum coherence to survive. Decoherence should destroy any quantum effects long before they could influence neural processing. But recent discoveries have shown that quantum coherence can persist in biological systems longer than previously thought. Photosynthesis uses quantum coherence to transfer energy efficiently. Bird navigation might involve quantum entanglement in molecules in the eye. These findings suggest biology can maintain quantum effects even in messy environments. Whether quantum processes are relevant for consciousness remains unknown, but it's not as obviously impossible as it once seemed. If a consciousness does involve quantum processes, then many worlds would apply to consciousness itself, with conscious states branching into superpositions that quickly decohere into separate experiential streams in different branches. The question of personal identity becomes even more puzzling when we consider consciousness and branching together. Before a branching event, there's one person with one stream of consciousness. After branching, there are multiple people, each with a continuous stream of consciousness, extending from the pre-branch person. Each post-branch person has memories of being the pre-branch person and feels like they're the same person continued. Are they all the same person, or have they become different people who share a common past? Philosophers have developed various theories of personal identity over centuries. Some argue personal identity requires physical continuity, that you're the same person over time because you have the same body or brain. But many worlds challenges this because branching creates multiple bodies, multiple brains, all physically continuous with the original. Some argue personal identity requires psychological continuity, that you're the same person because you have the same memories and personality. But branching creates multiple psychologically continuous streams, each with equal claim to being the original person. Many worlds pushes us toward a view of personal identity as a relation rather than a property. You're not a single entity that persists unchanged through time. You're a branching pattern of causally and informationally connected experiences. The person you'll be tomorrow isn't a single individual, but a cluster of related individuals in different branches, all continuous with your current state, all having equal claim to being your future self. Personal identity is a one-to-many relation in a branching universe, not a one-to-one relation as we ordinarily assume. This has implications for how we should think about caring for our future selves. Ordinarily, you care about your future self because they'll be you, experiencing whatever consequences result from your current choices. But in many worlds, your future consists of many selves in different branches. Should you care equally about all of them, weighted by their amplitude? Should you focus on the high amplitude branches where your future selves are most likely to have significant measure? These questions touch on decision theory and ethics in ways that philosophers are only beginning to explore. The experience of making decisions feels like choosing between futures, selecting one path rather than another. But many worlds says all paths actually occur. You don't choose between futures in the sense of making some possible and others impossible. Instead, you determine properties of the branching structure, affecting the amplitudes of different branches, and thus the distribution of your future selves across different outcomes. This preserves a meaningful role for choice, while acknowledging that all quantum mechanically possible outcomes actually happen. Some people find this liberating. You don't bear sole responsibility for which outcome occurs, because all outcomes occur. If you make a decision and it turns out badly in your branch, at least other versions of you made different choices in other branches. Other people find it disturbing. Your choices seem less meaningful if all alternatives also happen. The unique path you thought you were forging through life dissolves into an impersonal branching structure, where every possible path is taken. The subjective weight of decision-making might shift when you internalize that you're not choosing a single future, but weighting a probability distribution of futures. The question of whether you have free will in a branching universe has generated extensive philosophical debate. Compatibilists argue that free will is compatible with determinism, that you have free will as long as your actions follow from your desires and reasoning, without external compulsion. Many worlds is deterministic at the level of the universal wave function, but produces apparent randomness at the level of individual observers. From your perspective within a branch, quantum outcomes appear random, giving the impression of an open future with multiple possibilities. But from the universal perspective, all possibilities deterministically occur through branching. This might provide the best of both worlds for free will. You experience making free choices between open possibilities, but the universe deterministically realizes all possibilities through branching. You're not predetermined to make one specific choice because you make all possible choices in different branches. Yet your choices are determined in the sense that the branching structure follows lawfully from the universal wave function and the Schrödinger equation. Whether this satisfies intuitions about free will depends on which aspects of free will you consider essential. Libertarians about free will who think free will requires genuine metaphysical indeterminism, with multiple possible futures, only one of which will be actual, might reject many worlds as deterministic. If all futures occur, there's no sense in which you could have done otherwise than you did. Every possible action you could take is taken by some version of you. But compatibilists can accept many worlds while maintaining that you have free will. Your choices are free in each branch because they follow from your character and reasoning. The fact that other versions make different choices in other branches doesn't undermine the freedom of your choices within your branch. The relationship between consciousness and quantum measurement has been experimentally investigated to some degree. If consciousness causes collapse or plays a special role in quantum mechanics, we might expect to see differences between measurements made by conscious observers versus unconscious apparatus. Experiments have tested this by comparing quantum interference patterns when humans observe which path a particle took versus when automated equipment records the path without human observation. The results consistently show no difference. Conscious observation doesn't affect quantum phenomena differently than unconscious observation. This supports many worlds' claim that consciousness is not special quantum mechanically. The experience of time and memory also relates to branching in interesting ways. You remember the past but not the future, which seems obvious but requires explanation. In many worlds, your memory of past events reflects that all current branches share a common past, a unified trunk from which all branches emerged. Your current brain state contains information about past events encoded in neural structures. This information is reliable because decoherence created stable classical records that persist across branches. But your brain doesn't contain information about future events, because those events haven't happened yet, in the sense that they're spread across multiple branches with different outcomes. The asymmetry between past and future thus reflects the asymmetry of branching structure. The past is singular, the future is plural. You can remember the one past you came from, but you can't remember the many futures you're branching into, because those futures don't exist as definite facts yet. Each branch will have a different future, and you'll remember whichever future your branch experiences. But you can't now access information about which branch you'll experience, because all branches are equally part of your future. Quantum mechanics has sometimes been associated with mystical or spiritual ideas about consciousness creating reality, or observers collapsing wave functions through mental acts. Many worlds firmly rejects these associations. Consciousness doesn't create reality or collapse anything. Reality is the universal wave function evolving according to physical law. consciousness is one type of pattern that occurs within this reality. Our observations don't bring the world into existence, or select which outcomes become real. All outcomes become real through branching, and consciousness simply experiences whichever outcome occurs in its local branch. This demystification of consciousness' role might seem disappointing to those who want quantum mechanics to validate ideas about mind over matter or consciousness as fundamental to reality, but it's intellectually honest and respects the evidence. Nothing in quantum experiments suggests consciousness has special powers or operates outside physical law. The measurement problem that troubled early quantum mechanics is solved by decoherence and branching, not by invoking consciousness as a special collapsing agent. Consciousness is important and mysterious, but its mystery is the hard problem of subjective experience, not any special quantum mechanical status. The future of consciousness research might reveal deeper connections between quantum mechanics and subjective experience, or it might show that consciousness operates purely through classical neural processes, with quantum mechanics irrelevant for understanding how brains generate experience. Either way, Many Worlds provides a consistent framework. If consciousness does involve quantum processes, it branches along with those processes. If consciousness is classical, it still branches because classical systems are ultimately quantum systems whose branching has been masked by decoherence. The branching of consciousness follows from the branching of the physical systems that implement consciousness, whatever those systems turn out to be at the deepest level. Chapter 9. Criticisms, Alternatives, and Ongoing Mysteries. Despite growing support among physicists, Many Worlds remains controversial and faces serious criticisms from both scientific and philosophical perspectives. Understanding these objections and the responses to them is essential for appreciating the interpretation's strengths and limitations. No interpretation of quantum mechanics is without problems, and intellectual honesty requires acknowledging where Many Worlds struggles to provide satisfying answers. The preferred basis problem stands as one of the most significant technical challenges. Quantum superpositions can be described using different basis states, and mathematically these descriptions are equivalent. An electron can be in superposition between spin up and spin down, or equivalently between spin left and spin right, or between any other pair of orthogonal spin directions. These are just different mathematical representations of the same quantum state, but physically they seem to correspond to different branching structures. Does reality branch into spin up versus down outcomes, or spin left versus right outcomes? The question matters because different bases would create different worlds with different observers having different experiences. Decoherence theory largely resolves this problem by showing that the environment selects a preferred basis through the dynamics of environmental interaction. Certain states, called pointer states, remain stable under environmental entanglement, while other states rapidly decohere. For macroscopic objects in typical environments, position tends to be a pointer state while momentum decoheres quickly, which is why we see objects with definite positions rather than definite momenta. The branching occurs in the basis selected by environmental decoherence, not in arbitrary mathematical bases we might choose for convenience. But critics argue this solution isn't complete. The Ein selection process that identifies pointer states depends on the specifics of how systems interact with their environments. Different environments might select different pointer states. In principle, one could engineer environments that make unusual states stable, creating branching in unexpected bases. Does this mean the branching structure is somewhat arbitrary, dependent on environmental details that might have been different? Or is there something fundamental about the environments that actually exist in our universe that selects natural pointer states? Many worlds advocates respond that pointer states aren't arbitrary because they reflect robust dynamical properties of how quantum systems interact with realistic environments. The fact that position is a pointer state for macroscopic objects isn't an accident or human choice. It's a consequence of how gravitational, electromagnetic, and other interactions work. In our universe, with its specific laws of physics, decoherence naturally selects certain states as stable, and these are the states that define the branching structure. The preferred basis is preferred by physics, not by us. The probability problem remains philosophically contentious, even with proposed solutions like decision-theoretic approaches. In many worlds, all outcomes occur. So, what justifies using quantum amplitudes as probabilities? If both spin up and spin down definitely happen, why should I assign 70% credence to one and 30% to the other based on their amplitudes? The answer involves arguments about rational credence and self-locating uncertainty, but not everyone finds these arguments convincing. David Deutsch's decision-theoretic derivation shows that a rational agent who cares about all their future branches should weight them by amplitude when making decisions. Hilary Greaves and David Wallace have refined this approach, showing that standard decision theory applied to branching scenarios naturally produces Born rule probabilities. But critics object that these derivations assume what they're trying to prove. They build in assumptions about rationality, or about how to count branches that already presuppose Born rule probabilities. If you reject those assumptions, you can reject the derivation. Some philosophers argue the probability problem reveals a deep flaw in many worlds. If all outcomes occur, there's no genuine probability, no real chance that one outcome happens rather than another. Probability language becomes a kind of useful fiction, a way of talking about amplitude weights without admitting that it's not really probability in the ordinary sense. This might be acceptable as an instrumental interpretation of quantum mechanics, treating it as a tool for predictions rather than a description of reality, but it undermines the realist reading of many worlds, where all branches are equally real. Defenders respond that probability in many worlds is about self-locating uncertainty rather than objective chance. Before a quantum measurement, you don't know which branch you'll find yourself in. After branching, all versions of you exist, but you have uncertainty about which version you are. This uncertainty should be calibrated to branch amplitudes by principles of rational credence. The probability isn't about which outcome happens. It's about which outcome you'll experience, and all outcomes are experienced by different versions of you. The question of testability raises fundamental issues about scientific methodology. Many worlds makes the same empirical predictions as other interpretations for all experiments we can perform. By construction, interpretations of quantum mechanics agree on probabilities for measurement outcomes, because they're all interpretations of the same mathematical formalism. Where they differ is in claims about what exists between measurements and what the wave function represents. If interpretations make identical predictions, how can we test which one is correct? And if we can't test them, are interpretation debates scientific or merely philosophical? Karl Popper, the influential philosopher of science, emphasized falsifiability as the criterion for scientific theories. A theory is scientific only if it makes predictions that could be proven wrong by experiment. Many worlds seems to fail this criterion because it can't be falsified. No possible observation could prove that other branches don't exist. We can only ever observe our own branch, and our observations will always be consistent with many worlds, because many worlds predicts the same observations as other interpretations. This makes many worlds unfalsifiable, and thus unscientific according to Popperian standards. Defenders argue that falsifiability is too strict a criterion, and that many worlds can be evaluated using other scientific virtues like simplicity, explanatory power, and consistency with established principles. The interpretation makes the same predictions as alternatives, while requiring fewer assumptions and postulates. It unifies quantum and classical physics, where other interpretations create divisions. It resolves conceptual problems like the measurement problem more elegantly than alternatives. These are legitimate reasons to prefer an interpretation, even if it's not uniquely testable. Moreover, some physicists argue that many worlds does make distinctive predictions in certain contexts. Quantum computing might provide indirect evidence for many worlds because the many worlds picture naturally explains how quantum computers work. If quantum computers can solve certain problems exponentially faster than any classical computer, and this speed-up comes from exploring exponentially many computational paths simultaneously, where are all those computational paths, if not in parallel branches? Copenhagen interpretation struggles to explain quantum computational speedup without invoking something very much like many worlds branching under a different name. The ontological extravagance objection claims that many worlds violates Occam's razor by multiplying entities beyond necessity. If one universe can explain our observations, why postulate countless branches? Isn't the simplest explanation that only one outcome occurs, the one we observe, rather than that all outcomes occur in a vast proliferation of unobservable worlds? This objection appeals to ontological parsimony, the principle that theories should not postulate more things than necessary to explain the evidence. The response distinguishes between ontological parsimony and theoretical parsimony. Many worlds is extravagant ontologically, postulating vast numbers of branches, but it's parsimonious theoretically, requiring only the Schrödinger equation without additional collapse postulates. Copenhagen interpretation is parsimonious ontologically, keeping only one outcome, but extravagant theoretically, requiring both Schrödinger evolution and a separate collapse mechanism. Which kind of parsimony should we prioritize? Many worlds advocates argue that theoretical parsimony is more fundamental because it's about the principles and laws that generate what exists, not just counting how many things exist. Furthermore, the branches aren't really added to quantum mechanics. They're already there in the mathematics of the universal wave function, which contains all the components corresponding to different measurement outcomes. Copenhagen interpretation has to add a collapse mechanism to eliminate most of the wave function and keep only one component. Many worlds simply takes the wave function seriously and accepts all its components as real. In this sense, many worlds isn't multiplying entities but refusing to subtract entities that the mathematics says exist. The issue of non-locality presents challenges for all quantum interpretations. Bell's theorem proves that quantum mechanics violates local realism, the idea that objects have definite properties and that influences cannot travel faster than light. Experiments testing Bell inequalities confirm quantum predictions, showing that entangled particles exhibit correlations that can't be explained by any local realistic theory. Copenhagen interpretation embraces non-realism, saying particles don't have definite properties before measurement. Pilot wave theory embraces non-locality, allowing instantaneous influences through the guiding wave. Many worlds claims to preserve locality by denying that anything travels faster than light during entanglement measurements. When you measure one particle of an entangled pair, you branch into outcomes corresponding to different measurement results. Your measurement doesn't affect the distant particle or cause the distant observer to get a particular result. Instead, the distant observer also branches, and the branching structures of your measurements are correlated through the initial entanglement. Each branch pair was determined by the original quantum state, not by faster-than-light signals between measurement events. But critics argue this explanation is subtle and perhaps too clever. The correlations between distant measurements still require explanation, and many worlds explains them by appeal to a universal wave function that somehow coordinates branch structure across space. This wave function is non-local in the sense that it's defined on configuration space rather than ordinary three-dimensional space. Whether this constitutes true locality or merely redefines locality in convenient ways remains debatable. Many worlds preserves locality in some senses, while arguably violating it in others. Alternative interpretations compete with many worlds by offering different solutions to quantum mysteries. The pilot wave or de Broglie-Bohm interpretation adds hidden variables specifying particle positions and momenta at all times. The quantum wave guides these hidden variables, but the variables themselves are what's real and definite. This interpretation is deterministic, agrees with all quantum predictions, and explains why we observe definite outcomes without requiring branching or collapse. It's been developed into a sophisticated research program with applications to quantum field theory and cosmology. Many worlds advocates argue pilot wave theory is less parsimonious because it adds hidden variables and guiding equations beyond what appears in standard quantum formalism. It also has to accept non-locality explicitly, with the guiding wave instantaneously affecting particle velocities across arbitrary distances. And it faces its own measurement problem in explaining why we only observe the particle's actual positions, rather than the wave that's supposedly equally real. But pilot wave supporters counter that their interpretation provides clearer ontology and more intuitive physics than many worlds' incomprehensible branching structure. Objective collapse theories like GRW propose that wave functions spontaneously collapse with tiny but non-zero probability even without measurement. Individual particles collapse so rarely it's undetectable, but macroscopic objects with many particles collapse rapidly, explaining why we don't observe superposition at large scales. These theories modify quantum mechanics in testable ways. Experiments can search for the spontaneous collapse events and measure their frequency. So far, no collapses have been detected, and experimental constraints have ruled out some parameter values that GRW models proposed. This makes objective collapse theories more falsifiable than many worlds, which might be seen as a virtue. But it also means they're riskier proposals that could be definitively proven wrong. Many worlds advocates argue that modifying quantum mechanics should be a last resort. We should first try to understand what quantum mechanics already says before adding new mechanisms. Only if many worlds or other no-collapse interpretations prove inadequate should we consider changing the equations. And, so far, no experiment has required modifications to standard quantum mechanics. QBism, or quantum Bayesianism, takes a radically different approach, treating quantum states as representations of subjective beliefs rather than objective reality. The wave function describes an agent's credences about measurement outcomes, not the actual state of physical systems. Different agents can assign different wave functions to the same system based on their different information, and both can be correct from their respective perspectives. Measurement updates beliefs through Bayesian inference, with quantum mechanics providing the rules for rational belief updating. Many worlds advocates find QBism unsatisfying because it seems to make physics too subjective and fails to explain why quantum mechanics works so well. If wave functions are just beliefs, why do different observers agree so precisely on measurement statistics? Why does quantum mechanics accurately predict experimental results? Cubists have responses involving intersubjective agreement and the structure of experience, but many physicists prefer objective realist interpretations that treat the wave function as describing actual reality rather than subjective knowledge. The relational interpretation developed by Carlo Rovelli proposes that quantum properties are fundamentally relational, existing only relative to particular observers or reference frames. There's no absolute fact about a particle's spin, only facts about its spin relative to specific measurement systems. This interpretation denies that wave functions collapse, but also denies that all measurement outcomes exist absolutely. They exist relatively, true for some observers but not others, without contradiction. This has some affinity with many worlds, but differs in its relativization of quantum properties, rather than absolutizing all branches. The many-minds interpretation, proposed by David Albert and Barry Lower, combines many worlds with a special role for consciousness. Physical reality branches as many worlds describes, but consciousness doesn't branch. Instead, each mind randomly follows one branch, with probability determined by quantum amplitudes. This preserves genuine probability and explains why you experience one outcome rather than superposition, but it requires minds to be non-physical entities that aren't governed by quantum mechanics. Most physicists reject this dualism as incompatible with neuroscience and the principle that everything physical is quantum mechanical. Experimental proposals to distinguish interpretations continue to be developed, though most remain technologically unfeasible. One suggestion involves creating quantum superpositions of sufficiently large objects that different interpretations might make different predictions about their behavior. If consciousness causes collapse, as some interpretations suggest, we might be able to test this by comparing measurements made by conscious versus unconscious systems. If an objective collapse occurs at some mass or complexity threshold, sufficiently sensitive experiments might detect it. If many worlds is correct, we should be able to maintain superposition in arbitrarily large systems, given sufficient isolation from environmental decoherence. Some researchers speculate about detecting other branches through subtle interference effects, or finding evidence of branch interactions under special circumstances. These proposals are highly speculative and face enormous technical challenges. The decoherence that separates branches is extraordinarily rapid and effective, making branch interaction essentially impossible with the foreseeable technology. But they illustrate that many worlds, while difficult to test, isn't completely insulated from empirical investigation. The philosophical literature on many worlds is vast and contentious, with detailed arguments about probability, identity, decision theory, and metaphysics. Professional philosophers who specialize in philosophy of physics have written extensively on these issues, and there's no consensus. Some philosophers defend many worlds as the most scientifically respectable interpretation. Others critique it as conceptually confused or empirically unmotivated. The debate continues with increasingly sophisticated arguments on both sides. What emerges from this survey of criticisms and alternatives is that no interpretation is problem-free. Copenhagen interpretation has the measurement problem and the unclear boundary between quantum and classical. Pilot wave theory has non-locality and additional structure beyond standard quantum formalism. Objective collapse theories require modifying quantum mechanics and haven't been experimentally confirmed. Cubism makes physics too subjective for many physicists' tastes. Many worlds has the probability problem and ontological extravagance. Every approach has costs and benefits, and choosing between them involves weighing different theoretical virtues and philosophical commitments. Many worlds' position in contemporary physics reflects this complexity. It's no longer dismissed as too bizarre to consider seriously, but it hasn't achieved consensus status either. It represents one major research program in quantum foundations, with significant support from prominent physicists and philosophers, but also substantial opposition from others who find alternative interpretations more attractive. The interpretation you find most compelling probably depends on which problems you think are most important and which solutions you find most satisfying. Chapter 10. Living in a Branching Universe. The meaning it all holds. What does it mean for how you should live your life if the many worlds interpretation describes reality accurately? The implications extend far beyond abstract physics into practical wisdom about decision-making, meaning, and how to navigate existence in a branching universe. Whether or not you're convinced that many worlds is correct, contemplating its implications can shift your perspective on choice, responsibility, and what makes this particular branch of your life valuable. The first and most important realization is that your choices matter in exactly the way they've always seemed to matter. You might think that if all possible outcomes occur across different branches, your decisions become meaningless. Why agonize over choices if every option gets taken somewhere in the branching structure? But this reasoning is backwards. Your choices don't determine whether certain outcomes occur. They're already occurring in all quantum, mechanically possible branches. What your choices determine is which branch you'll experience, which version of you will have, which experiences and consequences. From your perspective within this branch, you only get one path through reality. The other branches are real, but they're not accessible to you. You can't visit them, can't experience their outcomes, can't help the versions of you living in different branches. Your responsibility is here, in this branch, making choices that shape this particular continuation of your consciousness. The fact that other versions exist elsewhere doesn't diminish the importance of living well in the branch you inhabit. If anything, it amplifies it, because your choices ripple through the branching structure, affecting the distribution of your future selves across different qualities of life. Think about decision-making through the lens of many worlds. When you face a choice, you're not selecting a single future from alternatives that will cease to exist. You're determining the amplitudes of different branches, making some future paths more weighted, more significant, more real in a measure-theoretic sense than others. Good choices increase the amplitude of branches where you and others flourish. Poor choices increase the amplitude of branches where suffering and regret dominate. You're not just choosing for yourself in this moment. you're influencing the entire tree of your future selves and their relationships with others across the branching structure. This creates a kind of probabilistic ethics. You should make choices that maximize expected value across your future branches, weighted by their quantum amplitudes. This sounds abstract, but it translates into practical wisdom. Take care of your health, because this increases the amplitude of branches where you remain healthy and vigorous. Cultivate meaningful relationships because connection and love enrich branches throughout your future tree. Develop skills and pursue purposeful work because capability and meaning improve the quality of countless future branches. Act with integrity because betraying your values corrupts not just one future, but a whole distribution of futures across branches where your character development follows from your current choices. The perspective also provides a healthy relationship with regret. When you make a decision that turns out badly in your branch, it's natural to wish you'd chosen differently. But in many worlds you did choose differently in other branches. There are versions of you who made the choice you wish you'd made, living the life you wish you were living. This doesn't erase your regret in this branch, but it contextualizes it within a larger structure where all possibilities actualize. You're not uniquely cursed by your choice. You're experiencing one outcome from a distribution that includes both better and worse results. This can reduce the paralysis that sometimes comes with regret. You made a choice with the information and judgment you had at the time. In this branch, it led to negative consequences. In other branches, perhaps it led to positive consequences, or different choices led to different outcomes. The branching structure contains all these variations. Your task now isn't to dwell on alternate histories, but to make the best choices going forward from your current situation. The future remains open with countless branches stemming from each moment. Past regrets don't determine future outcomes, except through how you let them affect your current choices. Similarly, success and achievement should be held with appropriate humility. If things go well for you in this branch, if you accomplish goals and experience good fortune, remember that chance played a role. Quantum events that could have gone differently did go differently in other branches. There are versions of you who worked just as hard but encountered bad luck, quantum or otherwise, that derailed their plans. Your success in this branch is real and worth celebrating, but it's one outcome from a probability distribution that includes both successes and failures. This should cultivate gratitude rather than arrogance, appreciation for being in a fortunate branch, rather than presumption that you uniquely deserved success where others failed. The many worlds perspective can also influence how you think about other people. Everyone you encounter is facing the same branching reality you are. They're making choices that split them into multiple versions experiencing different outcomes. When someone makes a choice you disagree with or that harms you, remember that other versions of them made different choices in other branches. The person before you in this branch made one choice, but the full person includes all their branches, most of which you'll never encounter. This doesn't excuse harmful behavior, but it might cultivate compassion by recognizing that identity is more complex and multifaceted than single-branch interactions suggest. In relationships, many worlds adds poignancy to the connections we form. The people you love in this branch are shared presences across vast swaths of your branching structure. In countless branches, you have similar or identical relationships with them. In other branches, your paths diverged. Relationships ended or never began, different people entered your life. The particular configuration of relationships in this branch is one realization from many possibilities. This makes the connections you have here precious. This specific relationship with this specific person in this specific branch is unique, even though similar relationships exist in other branches. The qualia of this particular experience of love or friendship or family belongs only to this branch. Death takes on complex meaning in a branching universe. When someone you love dies in your branch, they continue living in other branches where quantum events played out differently. Perhaps in some branches they were never born, or died earlier, or will live much longer. The full reality of their existence spans all these branches. But the version you knew, the specific person shaped by the specific experiences of the branch you shared, is gone from your branch. You lose access to their presence, even though versions of them continue elsewhere. The grief is real because the loss in your branch is real, even if continuations exist in branches you cannot access. Your own mortality follows similar logic. In some branches you die young. In others, you live to old age. In rare branches with improbably fortunate quantum events, you might survive circumstances that kill you in most branches. From your subjective first-person perspective, you only experience the branches where you survive, which creates the unsettling possibility of quantum immortality. But this shouldn't encourage recklessness. Most of your future measure exists in branches where you take reasonable care of yourself and live to expected lifespans. The low-amplitude branches where you survive improbable dangers aren't where most of your future existence resides. The question of meaning becomes more subtle in many worlds. If every possible outcome occurs, does anything really matter? If all paths are taken, is any path more meaningful than others? The answer depends on what you think creates meaning. If meaning comes from uniqueness, from the irreplaceable singularity of events, then many worlds might seem to diminish meaning by multiplying everything across branches. But if meaning comes from the quality of experience, from consciousness recognizing and appreciating value, then many worlds doesn't reduce meaning at all. Every branch contains real experiences with real meaning for the consciousnesses within that branch. Moreover, the branching structure itself might generate a kind of meta-meaning. You're not just living one life, but participating in a vast exploration of possibility space. The full reality of who you are spans all your branches, exploring different paths, making different choices, experiencing different outcomes. This totality has a kind of richness and depth that single timeline existence wouldn't possess. You're simultaneously the version reading these words and countless other versions living different lives, together forming a complete picture of what your life can be given, the starting conditions and quantum possibilities available to you. The relationship between many worlds and spirituality is complicated. The interpretation itself is purely physical, making no appeals to supernatural forces or non-material substances. Everything, including consciousness, emerges from the quantum wave function evolving according to physical law. This might seem to leave no room for spiritual meaning or transcendent purpose. Yet some people find many worlds strangely spiritual in its implications. The unity of the universal wave function underlying the apparent diversity of branches echoes mystical insights about the unity of all existence. The recognition that your individual perspective is one component of a vast, interconnected structure resonates with spiritual teachings about transcending ego and recognizing deeper connection. The many worlds framework also connects to questions about the purpose of existence that have occupied philosophers and theologians for millennia. Why does anything exist rather than nothing? Many worlds doesn't answer this ultimate question, but it reframes it. The universe isn't a single trajectory from beginning to end, but a branching exploration of all possible trajectories, consistent with physical law. Perhaps existence itself is inherently exploratory, reality investigating its own possibilities through the branching structure. Consciousness might be the universe's way of experiencing and appreciating this exploration from within. This connects to ideas about cosmic self-knowledge that we explored earlier. If the universe is fundamentally mathematical or informational, and if consciousness emerges naturally from complex information processing, then perhaps the branching structure is how cosmic information explores and knows itself. Each conscious observer is a perspective through which the universe examines one particular path through possibility space. The totality of all observers in all branches would constitute something like the universe's complete self-knowledge, knowing itself through every possible perspective and experience. Whether you find this satisfying depends on your philosophical temperament. Some people need purpose and meaning to come from outside the physical universe, from a transcendent source that gives existence its significance. For them, many worlds might seem too cold and mechanical, reducing everything to impersonal quantum dynamics. Others find meaning in the structure itself, in being part of a vast, self-organizing cosmos that generates complexity, consciousness, and the capacity to understand its own workings. For them, many worlds enhances rather than diminishes the wonder of existence. Practically speaking, how might you live differently if you fully internalized many worlds as your understanding of reality? You might approach decisions more carefully, recognizing that you're shaping probability distributions across your future branches rather than selecting single outcomes. You might cultivate equanimity about outcomes, knowing that all quantum possibilities actualize somewhere even though you only experience one. You might feel both more responsible, because your choices genuinely matter for shaping the branching structure, and more humble, because chance and quantum randomness influence outcomes beyond your control. You might also develop a different relationship with possibility itself. Instead of thinking about roads not taken as lost opportunities that no longer exist, you could recognize that those roads were taken in other branches. The life you didn't live isn't a mere counterfactual, but a real life being lived by another version of you. This doesn't mean you should abandon your current path, but it might reduce anxiety about having made wrong choices. You made all possible choices across branches. The question is how to proceed optimally from your current position in this branch, not whether you should have chosen differently in the past. The relationship between many worlds and free will can be understood in practical terms. Regardless of whether the universe is deterministic at the level of the universal wave function, your experience within a branch includes genuine deliberation and choice. You weigh reasons, consider options, make decisions. These decisions have real consequences in your branch. The existence of other branches where you chose differently doesn't undermine the reality of your choice-making process in this branch. Your decisions are yours in the sense that they flow from your character, values, and reasoning. They're free in the sense that they're not externally compelled and they genuinely affect what happens next in your life. This compatibilist understanding of free will in many worlds suggests You should act as if your choices matter absolutely, because from your perspective within the branch, they do matter absolutely. You don't get to experience other branches or benefit from better choices made by other versions of you. Each version of you exists within their own branch and must deal with the consequences of their own choices. Thinking about other branches might provide perspective, but it shouldn't diminish the seriousness with which you approach decision-making in your own branch. The many worlds interpretation might also affect how you think about luck and injustice. When terrible things happen to good people, when someone suffers through no fault of their own, it's natural to ask why. Many worlds doesn't provide cosmic justice or moral order. Random quantum events distribute outcomes across branches without regard for who deserves what. Some versions of good people end up in fortunate branches. Others end up in unfortunate branches. The distribution follows quantum probabilities, not moral principles. This might seem bleak, but it's honest about the structure of physical reality, while still allowing for human-created justice and compassion within branches. Your responsibility is to create justice and reduce suffering in your branch, regardless of what happens in other branches. The fact that someone is suffering in your branch isn't balanced or justified by them flourishing in other branches. Their suffering here is real and demands moral response here. Many worlds doesn't provide theodicy or cosmic fairness, but it also doesn't require such things. Morality and meaning are constructed by conscious beings within branches, shaping how we treat each other and build societies, independent of whether the underlying quantum structure is fair or unfair. Looking toward the future, both personal and cosmic, many worlds suggests an open and exploratory orientation. Your future isn't predetermined to follow one path. It branches into countless paths, most of which you can't anticipate or control. The best you can do is make choices that increase the amplitude of good branches while remaining flexible and resilient when facing inevitable uncertainty. This is similar to wisdom traditions that emphasize preparation, virtue, and adaptability, rather than rigid planning or anxious attempts to control outcomes. On cosmic scales, the branching will continue as long as quantum events occur, which is presumably for as long as the universe exists. The structure grows ever more complex and diverse, exploring more and more of possibility space as time progresses. Whether this leads anywhere, whether there's any ultimate purpose or end point to the branching, remains unknown. Perhaps the branching continues eternally, endlessly creating new variations. Perhaps there are cycles or attractors or eventual convergences we can't currently imagine. The future, like the present, is ultimately mysterious despite all our physics and mathematics. The connection back to Emmy Noether's theorem brings the journey full circle. She discovered that symmetries in physical law correspond to conservation principles. Energy is conserved because physical laws don't change over time. Momentum is conserved because they don't change across space. These conservation laws reflect deep symmetries in the structure of reality. In many worlds, these symmetries and conservation laws govern how the universal wave function evolves and how branching occurs. The mathematical elegance Noether revealed underlies the branching structure of existence itself. This suggests that reality at its deepest level is governed by principles of symmetry and conservation, and that express themselves through the quantum branching we've been exploring. The universe isn't arbitrary or chaotic. It follows precise mathematical laws that determine what's possible and how possibilities actualize through branching. Understanding these laws as physicists and mathematicians continue to do, is understanding the source code of reality itself, and that understanding might ultimately reveal purpose and meaning woven into the structure of existence in ways we're only beginning to glimpse. Living in a branching universe means accepting radical uncertainty about which specific future you'll experience, while maintaining confidence that your choices shape the distribution of futures across branches. It means holding both humility about your place as one branch among countless others, and recognition that your branch is real and important. It means appreciating the preciousness of this particular path through reality, while acknowledging the vast tree of alternative paths that also exist. It means taking responsibility for your choices while recognizing that randomness and branching ensure no one achieves perfect control over outcomes. Most of all, it means embracing the profound mystery and beauty of existing as a conscious observer in a branching quantum universe. You are reality, knowing itself from one specific perspective, in one specific branch of an incomprehensibly vast structure. Your experiences, your relationships, your choices, your consciousness are genuine and meaningful, regardless of how many other versions exist in other branches. This moment, this branch, this experience of being you reading these words right now, is unique and irreplaceable, even in a universe of infinite branching. That's the gift and the responsibility of existence in a many-worlds universe. Still here, friend? If your eyes are getting heavy, it's okay to let them close. Your mind remembers the way. But if you're still awake, there's another video waiting for you. I'll be here if you'd like a little more company. Either way, thank you for spending your night here. May your dreams be calm, your breath gentle, and your thoughts float softly like stardust. Sleep well among the stars.